All right, so good evening, everybody. It's my pleasure to be invited here to talk to you today. I'd like to acknowledge that I'm speaking to you from Ngunnawal land, and I pay my respects to the Aboriginal owners of this country that was never ceded. And I would encourage everybody to reflect upon the lands that which they sit today. So the talk I'll be presenting is all about my research and what I've been doing, but I'll sort of put a little bit about what it's like being a physicist in a university, what research I do, what my day-to-day kind of job entails, and some other little tidbits. Hopefully make it a little bit interesting for you here on a Sunday evening. So for a start, this image. This is one of the favourite images of my research, and I hope you can see it, but it's got little bits of sticky tape from, can you see this in the side here? There's little bits of sticky tape there. This is actually just a screenshot I took on my iPhone of this this really old monitor that we were doing this experiment on, and this is a little bit of carbon that I've squeezed to really high pressures, and I'll talk to you about that in a little while. But what happened was when we were unloading it, it formed this beautiful interference pattern. So what we're doing here is we're looking through a diamond, and we're looking where it's sort of squashed against a bit of metal that we call a gasket. It's holding my sample in that I've made this new material, hopefully something really interesting. And we've just got a little bit of spacing between the diamond and the gasket, and it's formed an interference fringe because we've got a very thin spacing and the light interferes with itself and causes this beautiful rainbow effect. I love this, so I took a photo of it because I thought it was quite pretty. And I also liked the little bits of sticky tape on the end, and this ended up making the cover of a magazine because the editors also really liked the fact that it had the little bit of sticky tape on it. We were actually using it as a way of centering. You can see in the middle is a little cross we're using to center it, and we'll put a laser on there. So just something I snapped, but turned out to be quite a beautiful, beautiful image. So let's get underway. So what do I do? Okay, so my work is with some group 14 elements, and they are silicon, germanium, and carbon, and that's where they are in the periodic table. And what I do with these materials is I try to create new forms of the materials. So I started off with silicon, and what I was chasing was a new form of silicon that had a more efficient way of capturing sunlight. Now, you all know silicon is used in solar cells on roofs, and that type of silicon is only one allotrope, what's called an allotrope. Different crystal structures are different allotropes. And there's actually like 14 allotropes of silicon. So there's all these different things that we could do, but we've just chosen this one form of silicon for solar cells. So we actually found a few different forms of silicon that have better ways of capturing light. And we're investigating how to scale that up to maybe make a more efficient solar cell. I've also been doing some work on germanium, which is the next element down in the periodic table there. And that was sort of similar because they're like sister elements. They do similar stuff. If we could understand silicon, we could understand germanium. So that's what I did for quite a long time with my PhD and when I was an early researcher. But more recently, I've climbed back up the periodic table and ended up in carbon. I think carbon is probably my favorite element at the moment, and that's because it does some really, really interesting things. You probably know two forms of carbon already. Diamond graphite is sort of the common ones, but there's heaps of other forms of carbon too. So it's a very, very interesting material. So what I do is we try to make new crystals, and this is my recipe for making a new crystal. And I say a crystal, but I could also just say here new material, because actually most of materials have got a crystalline structure. Sometimes people are a bit surprised about that. They sort of think crystals are something like a crystal you might see in like a beautiful quartz crystal or something like that, quite large. But crystals, of course, are all around us. Things like your aluminium saucepans are also crystals. Nearly every metal you'll see will be a crystal. So really, this is a recipe for making a new material. We're just rearranging things, really, rearranging Lego parts to make a new picture. So I choose my starting material, and I like these nice pure elements. So I just choose a pure element from the periodic table, carbon that I'll be talking about today. I load it into a pressure cell, so work out some way to applying super high pressures to it. I'll add a pinch of ruby and gold, and that enables me to see what pressure that I'm measuring at. Squeeze it to really, really high pressures, and then unload it and try to measure my new crystal for what I got. And that pretty much captures what I do a lot of the time. But let me go into it in a little more detail. So this is my tools. So this is something called a diamond anvil cell. And this is really simple little thing. It can fit in the palm of my hand when I travel overseas to do experiments, which I used to do before COVID quite a lot, because I use these synchrotron X-ray sources. I would have maybe 10 of these in my backpack, all ready to sort of load into these synchrotron X-ray sources and measure my crystals. So I'd make them and measure them on the spot. And how this little device works, we just have two stainless steel plates. And right in the center there, I hope you can see my pointer, this is where the diamond sits. And you can see this is a schematic that one of my students drew. And you can see we've got two diamonds here, and they come together like this, and they squeeze the material in between. Now, because the diamonds are very, very hard, and the point of the diamond is very, very small, we can apply a reasonably high force, but not massive, just a high force. And we can apply that force, and it's focused into the very top of that diamond, and we can get an extreme pressure, and that's what we're after. So we're really creating materials under extreme environments. Part of the reason we use diamonds, of course, is because they're transparent. So we can shine things through them while we're doing it. And we often shine X-rays through them, so really intense X-ray sources. We have one of these sources down in Melbourne, the synchrotron. We've also got them all around the world, and the one I use mainly is near Chicago, because they have a specialist high pressure facility. So they have like a whole 3 what's called beam lines all set up for high pressure. So you go there and it's just like Christmas. It's everything that you could possibly want. It's wonderful. So we've done a few remote experiments since COVID, but I haven't been back there since October 2019, so it's a bit sad. And we put our sample in the middle of this little bit of metal here. There's got a tiny little hole in the middle, that's the gasket. And we're holding it in place in this picture here with some, usually we use blue tack, but it looks like we're using plasticine here, and it doesn't really matter what it is, just has to hold the gasket in place. So this is what I use to make my material. If you look at it in cross section, this is what it looks like. So you have the two diamonds and then the gasket in the middle, and the material's trapped in between the middle of all those things. So I use a lot of diamonds. As I said, one of the reasons we use it is because they're the hardest known material. So that's super important. And also because of their optical properties. We can literally see through them to see how the materials behave under pressure. So we load them with the diamonds, and then we shine light or X-rays through to see what's happening to that material as we apply these super, super high loads. Diamonds are also useful because they dissipate heat really well. They have a really interesting optical and thermal properties. So they're quite an amazing material. The pressures that we use can be thought about as force divided by area. And I've just put this there because I think in a lot of science and a lot of secondary science, sometimes you'll talk about pressure only as sort of a gas pressure. And it's the same type of thing. Gas pressure is just caused by all those little atoms running around and banging on the side of whatever container you're measuring, and that's the same as pressure. But what we're thinking about here is a force, so a load divided by the area. So if you have a really small area, you can get a really high pressure. And I just wanted to give you some pressure landmarks so you can think about how extraordinary the pressures that we're creating actually are. So first off, this is a relatively low pressure, but it's a sort of an everyday high pressure experiment, high pressure, that people do, making a cup of coffee. So when we make coffee, the extraction of the coffee is done at about 8 to 10 atmospheres, if it's a good coffee, so 8 to 10 times normal atmospheric pressure. This is the equivalent of 0.001 GPa. And this GPa, gigapascals, is the unit of pressure that I'm going to be talking in mostly today. A gigapascal is a billion pascals. So it's quite a large number. And that's why only 10 atmospheres is extremely small. So that's our first pressure landmark, very 0.001 GPa. The next one, we'll just go straight to the center of the Earth. So this is another pressure landmark, and physicists like this idea of landmarks. We like to have kind of these orders of magnitude things in our minds. Well, is it a big pressure? What's the pressure in the center of the Earth? How does it compare? So the center of the Earth has a pressure in gigapascals of about 360 GPa. So quite a high pressure in anyone's language. So my little diamond anvil cell that I showed you with the plasticine there can create pressures equivalent to the center of the Earth. And we've created pressures up to around 100 GPa in our lab. So this is what's achievable with a diamond anvil cell. It's pretty achievable to do 20 GPa. So if you were an undergraduate student, you've come to university and you might approach me to do a research project in my lab. And sometimes we have students that come and just work with us as part of their degree, or they might just kind of volunteer for a week or so to hang out with our lab and sort of see what we do. I might get them doing experiments like this. They might use this type of thing to make pressures of up to 20 GPa and make some interesting crystals at that pressure. At 50 GPa, it's starting to get a bit more difficult. This would be where my honours students and PhD students would do those experiments. And once we get up to 100 and over 100 GPa, this is where it actually gets pretty expensive. Because at those pressures, you're almost guaranteed to break the diamonds. And actually, it is a lot easier to break diamonds than one might first imagine. I think we think diamonds are super, super hard and therefore it's like impossible to break them. But that's not entirely true. Diamonds are, yes, very, very hard, but they're also quite a brittle material. So if you have two diamonds and you push them against each other and maybe they're slightly misaligned and the edge of one touches before the whole body does, it can crack. And when you start getting to loads above or pressures above 100 GPa, you break diamonds almost guaranteed. And this takes a little bit of getting used to. The first time we broke diamonds, it was a bit kind of upsetting. And now every time we break diamonds, it's still a bit of a sad moment, especially because they're not cheap and the students, know that we don't have a never-ending supply of them. So we try not to break them, but it's part of you sort of like have to crack eggs to make an omelette type of thing. We have to break diamonds to make diamonds, but we make new types of diamonds. So what pressures are we typically going to? So the first few elements that I was talking about, silicon and germanium, really interesting things happen and we can create all these different allotropes at only about 15 to 20 GPa. But with carbon, you need to go up around 100 GPa for things to happen. And this is where things get quite interesting and carbon changes its form quite dramatically. So here's the two forms of carbon that you're probably quite familiar with. So the picture of the diamonds at the top, everybody will identify those as diamonds. But when I think about diamonds, I think about it more like the picture at the bottom here. This is a representation of the carbon atoms arranged in what's called a diamond cubic structure. What I'm showing you here is what's called a unit cell. So it's a sort of a slice of a crystal that repeats to make the entire body of the crystal. And this is the smallest part of the crystal that you can get and repeat to build up that whole big crystal. The next lump of black stuff here is graphite. And that consists of these long sheets, like chicken wire type hexagonal sheets. And they sit on top of each other like this with some bonding between them, but not perfectly strongly connected. So they actually slide past each other really, really easily. So this is actually worth just pondering how interesting this is. What you've got here is a change in just the crystal structure of these materials. These little balls of atoms, they're exactly the same thing. We've just changed the way they're bonded and we get completely different materials. On the one hand, we get graphite, which is, you can't see through it. It's quite soft. In fact, it's in pencils because it's so soft, we can rub it off on paper. It's so soft. It's slippery. It slides past each other really well. On the other side, just by rearranging the positions of those atoms, we have diamond that is super hard, transparent, and very, very an interesting material. So one of the questions I like to ask is, well, what do you think is the most stable? Now, you could put it in the chat if you wanted to. You can put, if you want to kind of commit to your answer, you can put it in the chat. So which do you think is most stable? And I've put stable in little inverted commas there because it's sort of like, well, what do you mean by stable? And I'm sure many of you are asking that because that's what you would want to ask at this point. What do I mean by stable? And what I mean by stable is if you heat it, what will happen? So when we talk about a very stable material, it's something that can withstand really high temperatures, perhaps high pressures before anything else happens. So have a guess. Do you think diamond is more stable or graphite is more stable? I can't see the chat at the moment, but I'll look in at the end and see what you all think. And the answer is actually graphite. And this is often a bit of a surprise to people because they think, well, isn't like diamond the most like hard material and therefore the most stable? But actually it's not. Carbon likes to be in graphite. That's what we call the thermodynamically most stable material. So that means that you should not heat your diamonds. If you put diamonds in an oven, it will start to change. The carbon atoms at about 700 degrees start bonding with the atom of oxygen and will form CO2 and float off. And if you heat up diamonds to over 1,700 degrees, your diamonds start turning into graphite. So you don't want that. So the nature really prefers carbon atoms to be in the graphitic form. And what this actually means is every diamond on Earth is very slowly transforming back to its lowest free energy structure. But because it's stuck in what we call a local minima, it's really, really slow. In fact, the universe is not old enough for any diamonds to have actually done this, but theoretically it happens. And if we use temperature, we can speed up that process. And that's what I mean by being stable. What that means is if you take graphite and you try to get it back into diamonds, you need a lot of energy. When I talk about energy, I can talk about heat or I can talk about pressure. And it's sort of thermodynamically the same thing to a physicist. It might seem a bit strange to you, but it's very similar. So strictly speaking, sorry, James Bond and De Beers, diamonds are not forever. You can easily turn them back into graphite and you can easily break them. So can we make more than one form of diamond? We've talked about two forms of carbon already, the graphite and the diamond, but how about diamond? Can we make more than one form of diamond? Well, what do I mean by that? That sort of sounds a bit weird. So what I mean by that is diamond is arranged in a way where it's bonded with 4 other carbon atoms. And if we do that with a different crystal structure, so instead of having what's called the diamond cubic structure, that picture I showed you before, if we rearrange them so they're still connected to 4 atoms each, so there's still a diamond, but it's a different structure, we can get different forms. And in fact, we get this structure here on the right, which is called a hexagonal diamond instead of a cubic diamond. And actually, this is called Lonsdaleite. And this is what my team has found in recent times, which has been our kind of exciting new discovery. Now, Lonsdaleite, so this "ite" thing at the end here, this is a mineral naming convention. So it's named after somebody called Lonsdale. And actually, it's named after this lady here. So this is Kathleen Lonsdale. She was an Irish crystallographer and was one of the early crystallographers working on carbon. So this structure of carbon was named in her honor. And if you have some time, I would recommend Googling Kathleen Lonsdale and read about her amazing life. Her she's got these beautiful handwritten books of what's called structure factor tables. And this is really, really complicated crystallography, but it's basically describing where atoms are in a mathematical language. She wrote out the structure tables by hand, and it's a thing of great beauty, and it was very, very useful at the time. She also had some really interesting ideas around other forms of crystal structures of different materials. And actually one of the materials that we start with, she had the early idea about what it could be. So she's a very interesting person. So the material Lonsdaleite is super interesting for us because it's predicted to be 50% harder than normal diamond. Now, you probably all know that diamond is the hardest thing that we know of. Well, this is sort of like diamond 2.0. And it hasn't really been found much in nature. In fact, it's been a little bit controversial about if it exists at all. So it's previously been made in a lab, so synthesized, but not in a very pure way. And it's been found with graphite at really high temperatures. So that's how people have previously made it, and they found little glimpses of it. And they're like, oh, we think this is a thing. And then it was found in nature in tiny, tiny amounts at the site of meteorite craters. So this is the crater that it was first found next to. This is Canyon Diablo crater. This is it in Arizona in the US. And this is my family and I on holiday there. We went there for my one of my birthdays a few years ago, and we were going to other places, but I dragged everybody over to see this canyon because it was where Lonsdaleite was first discovered, and I thought that was very cool. And I actually got some earrings made out of some of the rocks I found in the area, so sometimes I wear those. In fact, I should have worn them tonight. So that's where it was found in nature. But we actually made the two types of diamonds, so both crystalline cubic diamond, sort of the normal diamond, plus this new hexagonal Lonsdaleite diamond, and we made them at room temperature for the first time. So this was some work that we released in November last year, and it got a lot of interest. We were sort of flat out doing media interviews and things for a few days, and it was a very, very exciting time. There was a lot of interest in our work because, one, we had shown that you can make diamond, just normal cubic diamond at room temperature, and we could also make it really quite quickly because we were just using this diamond anvil cell that my student Xing Shaw is holding up here, and we could just literally squash them together and we could make these two types of diamonds at room temperature really, really quickly. So why aren't I super rich and driving my sports car around instead of just, being a normal university teacher? Well, that's because we only make very, very small amounts of it at the moment, but it's a proof of principle, and that's a really interesting thing, and that's how science works. You kind of prove that it's possible, and then you work out how to optimize it to get more. And this is what we found. So what I'm showing you here is the little bit of material that we've recovered from this diamond anvil cell, and this is the tiny bit in the middle. So this is only a few hundred microns apart, so billionth of a meter is a micron, so a few hundred, so maybe 0.2 of a millimeter across here. And what we've done is we've used some special instruments. It's called a focused ion beam, which focuses beams of ions, so you can dig out things really, really accurately. And we've plucked out a very, very thin salami slice of material like this. And then we can use a microscope that, instead of uses light, uses electrons. And we look at the slice that we've created with these electrons, and we can see if we've created new forms of diamonds. So this is what our samples would look like, and this is what our final picture looked like. So what we found was essentially a river of nanodiamonds. So all these little bright particles in the middle here, these are all the diamonds, and they're floating in this sea of Lonsdaleite. And this was all made at room temperature quite quickly, but all of these things are very, very small, and each individual one is extremely small. It's a nanoparticle, so it has different properties to a macroscopic particle, and it has a lot of really, really interesting uses. But we've proved that we can make these two things together at room temperature for the first time. So I think this was probably the most exciting thing that's ever happened to me in terms of my career. It's probably the most exciting thing that ever will happen in terms of my career, but well, I live in hope, and maybe we'll do something else. But it was a very interesting and amazing finding. So this is, hold on. Oh, where's the picture of us? Oh, it doesn't want to pop up. Oh, you might have seen a glimpse of it. I had a picture of us here that we took a selfie when we first saw it in the lab for the first time. It took us about a year of pretty hard work to guarantee that that's exactly what we saw. And I've just taken a screenshot of a figure from the paper that we published here. So this sort of gives you an idea of the sort of scientific level of detail that you go into to kind of show what you've done in order to kind of publish that work and make an understanding of it sort of known to everybody. So how did we do it? What was the sort of the secret sauce associated with this process? Well, instead of just using pressure that I talked about before, or pressure and temperature, because we wanted to avoid temperature, because we know that diamonds actually just go back to graphite if you get too high temperatures, we used something called shear as well. So this is sort of like a different type of pressure. It's like a twisting pressure. So a good example of this is if you get a pack of cards and you push the top card around, you get this shearing effect here. And that's what we did to the carbon. And that made all the difference. So that enabled it to get into that diamond state and stay there without adding any temperature or anything else. So that was our kind of magic ingredient. If you want to read more about this work, we wrote a nice conversation article, which is sort of super easy to understand. So I would encourage you to just Google diamonds in the conversation and you'll see this article here. And you can get a bit of a more detailed understanding of it if you're interested. So what's next? What are we going to do next? Well, we need to make more of it. So we're going to be using bigger diamonds for even bigger samples. And this is some work we're doing in collaboration with an ex-student of mine who's now in the US. And they work with some groups that synthetically grow diamonds. So this big diamond here, this is a 10-carat diamond. This has been synthetically grown. So it's grown in something that's kind of like a microwave oven at a high temperature with some special gas flowing over it. And you get a seed crystal. And it's a little bit like that experiment you might have done in primary school where you put a seed crystal on a bit of string and you grew another crystal around it from a supersaturated solution. That's kind of how they grow synthetic diamonds. It's a very slow process, but they can grow beautiful big diamonds. So we're using these diamonds here to create really large samples. And instead of looking at them with X-rays, we're going to be looking at them with neutrons, which is better for us because they have a better cross-section or a better interaction. Neutrons have a better interaction with carbon than they do with X-rays for various reasons. So that's our next big thing. We want to create more of this material and understand the steps to creating it so we can do it more easily, cheaply, make more of it, and hopefully make it more achievable for a commercial process. So what does my research actually look like? Well, this picture here with me holding the hammer, this was taken at the end of a night shift where something had gotten stuck and they just said, well, excuse me, the beamline scientists, it was sort of 3 o'clock in the morning and they said, oh, well, we can't come and help you, maybe just whack it with a hammer. So this is the before picture where I got the hammer and we whacked it and it did get unstuck and we were able to continue with our measurements. The picture in the middle here, this is in my lab at the Australian National University. So this is a benchtop experiment. This little thing sitting up there is a new type of diamond anvil cell that we've designed that has a lot of twist to it. So what we're going to be doing is doing squashing and twisting to really force that shear and hopefully understand the formation of those materials a little bit more clearly. And the other pictures here are just pictures of me on various experimental runs. And the picture in there, there's that one of the big diamonds that we use. It's not a very pretty diamond because it's just not cut in a pretty way, but it's actually really large. Other aspects of my job, so I don't just work in the lab, I do a lot of other things as well. It was mentioned in the introduction that I was president of the Australian Institute of Physics, which is the professional body for physicists. So all the physicists join this body and we organise meetings and talks and lobby for physics in the country. So I was the president for 2 years, and this was the executive team that I led. Also really enjoy working with people, and it's nearly all teamwork. So my form of physics is all really working together. This is an experimental run that we did a few years ago with 2 of my PhD students. Both of these students are working now in jobs as scientists, but we all got together to do this experiment together, which was nice. Sometimes we do things a little bit weird. This is actually a mint slice, and we were asked to measure the mechanical properties of the mint slice when it was cold and when it was at room temperature to see if there was a difference to the mouthfeel. So that was quite a fun project. This is a student that I mentored for many years, Siobhan, who's got a Rhodes Scholarship and has gone off to the University of Oxford and doing a PhD in physics there. We were on the radio together, so that was a nice selfie moment. And finally, there's a lot of travel involved in my job, which, well, there was a lot of travel involved in my job, which I really, really enjoyed. So it was sort of like an unexpected aspect of science, how international it is and how connected you are to all the other scientists. And of course, I am a lecturer as well. So this is me, second semester last year, just starting off our new season, lecturing in a mask because of COVID. So that's all I was going to talk to you about today. So thank you very much for the opportunity to speak. I'm leaving you here with an image of a broken diamond. I said in my talk, making and breaking diamonds all in a day's work, and we don't break diamonds every day, but we do break them fairly frequently. This one here was broken on the 23rd of May 2019 after we got to a pressure of 110 GPa, so that's that billion of pascals. And we actually think this is an Australian record. So we think this is the highest pressure ever achieved in a lab in Australia. And the diamond died, unfortunately, but it died in this beautiful moth shape here. So we're looking down the tip of the diamond. This is that little flat bit that we squash the material against. And we've got this great big crack kind of deep in here. But I think it looks a little bit like a moth. And the actual diamond itself still looks okay. So I'm going to have that made up into some jewelry for the student when she leaves and give it to her when she gets her PhD. So, okay, so that's all I had. So thank you very much for your attention.